Hello everyone, the following is a video demonstration presented in favor of the partial fulfillment of the requirements for the degree of Bachelor of Technology by Shrabanika Kashyap and Bikash Kalita under the supervision of Mr. Opurba Bikash Kalita, Professor Kondorpa Kumar Sharma and under the co-guidance of Dr. Surajit Deka. The topic of our project work is optimal design of low noise amplifier using multi-objective BET algorithm. Our project basically falls under the category of device optimization. Device optimization is a process by which we can maximize or minimize some function relative to some set, often representing a range of choices available in a certain situation. The function allows comparison of the different choices for determining which might be best. So, the main objective of this work is to find the optimal value of our objective functions, that is maximizing the gain and minimizing the noise figure of an LNA by the hybridization of multi-objective BET algorithm with the NSGA2 technique to design a CMOS cascade LNA. Then we will obtain the Pareto fronts as well as the design parameters of the objective functions, after which we need to design an LNA circuit in Cadence to implement the design parameters obtained from the MATLAB simulation in the LNA circuit. The goal is to eventually create a technique to cope with constraint optimization problems. This technique is based on feasibility segregation, non-dominated sorting and crowding distance adapted from non-dominated sorting genetic algorithm 2 technique. The non-dominated sorting is a technique by which a population of candidate solution is sorted into different fronts based on their dominance relationship. In other words, we can say that the set of solutions obtained by using the non-dominated sorting technique are the optimum set of solution and is not dominated by any other set of solution. The crowding distance measures the density of solutions under a particular solution with a specific front. It helps the algorithm to favor solutions that are not well represented and prevents the population from converging prematurely in a single area of the Pareto front. The larger the crowding distance, the more likely it is to be retained in the next generation of the evolutionary algorithm. Feasibility segregation is basically a technique which involves segregating the feasible and infeasible solutions in different populations. The goal is to handle the feasibility and optimality aspects separately. Here is a flowchart of how we have hybridized the BET algorithm with NSGA2 technique. We start the optimization process by initializing the BET population, after which we set the parameters. The sorting of parameters in terms of feasibility segregation, non-dominated sorting and the crowding distance is done. After which the code will run the loop to update the solutions, and as soon as the maximum number of iterations has been reached, the resulting hybrid algorithm, that is the non-dominated sorting BET algorithm with feasibility segregation, are then employed to solve the two benchmark multi-objective constraint problems along with obtaining the Pareto front. Here are the two objective functions that we need to solve by using our code. First, we have to maximize the gain and then minimize the noise figure of the given common source cascade CMOS cascade LNA that we can see at the center of the screen. To run the code, we need to pre-specify certain process parameters as well as limiting values of the design parameters. Here we have already pre-specified the given design parameters for our code. Also, pre-specification of control parameters for the BET algorithm is also to be made. This is the code which we have built to cater to our main objective. It has been hybridized with various techniques that we have employed, like the non-dominated sorting, crowding distance technique, normalization technique, and the replacement technique. The normalization technique is basically transforms the output to a similar set, whereas the replacement technique replaces the old solution of an updated solution, which is better. Also, here is the objective function which we have employed in our code to find the uh, two objective functions of our problem. Here we can see that we have pre-specified our design parameters, as well as we have also given the equation to as to how to find the two objective functions, that is the gain and the noise figure. So let us try running the code and obtain the Pareto front. Here we have successfully obtained the Pareto front of our objective functions. So for 1,000 iterations, the code has given us 100 pairs of optimal solution for our objective functions. So each of these pair are the optimal solution for our objective function, and choosing any one of these pairs will give us the optimal solution and design parameters for our LNA. Each of these pairs are the best solutions which are not being dominated by any other solution. The code also gives us the optimal design parameters to design the proposed LNA. Here we can see that for 1,000 iteration we are given 100 pairs of our objective function, first the gain and then the noise figure. Also we are given the process parameters, which are the width and drainage current for the CMOS. Therefore we can choose any instance from here randomly, and after putting that the value of that instance in our design circuit, we can obtain similar values as given by the MATLAB code. So let us choose the instance 24 randomly. Here is a table for the outputs for design parameters and objective functions for designing the LNA. We have obtained these outputs by doing back calculations by using the design parameters which were given by the MATLAB code. Now let us try implementing these design parameters in the LNA circuit in Cadence, which has been already designed by us. So let us first save this circuit, then launch the ADEL window. Then we will give the inputs for our first objective function, which is the gain. Since a gain is also represented by the S parameter to 1, so we will find out the S parameters. So first we need to select the ports. Then give the frequency range. We will run the simulation. So the simulation has completed. Now we can find the gain for our objective function. Since we need the gain, so we will choose the S21 parameter. So here the gain is almost a 50 decibel. As we can see from here, it is 24.8 decibel. But since we are using software which only supports the 90 which is 90 GPDK version of the cadence. So that's why this is one of the limitations in our project work. Since we have already chosen the S parameter, so we can also find out the other S parameters as well, like the S11 parameter, which is the input matching, minus 22.6 dB, the S12 parameter, which is the reverse isolation parameter, which comes out as minus 42.4, and the S22 parameter, which is the output matching parameter, which comes out around 0.3 dB. Now let us find out the noise figure for the LNA. For the chosen instance, the noise figure is 1.22 dB. So let us do the simulation in the cadence software. So let us first save the circuit. Since we have already found out the S parameters, so we can also find out the noise from the S parameter only also. But we need to change the sweep range for the noise figure. We have to select the output and the input port. Apply. Okay. Now we will run the simulation. And now we can get the plot for the S parameter, for the noise figure. So here the noise figure is coming out at 1.69 dB, which is almost equal to what our MATLAB code has given. So we can conclude that we have successfully proposed and implemented the hybrid multi-objective constraint BET algorithm, that is, the NSBAFS, have been used to solve the constraint benchmark optimization problem. We have also obtained the Pareto fronts of the problem and implemented the design parameters obtained from the MATLAB simulation in the LNA circuit. The output from the MATLAB as well as the cadence software are also found to be almost same. So this marks the ending of our project work. Thank you.